Hello everyone and welcome back to your YouTube channel and welcome to this very simple but exciting numerical example. As you must be aware, I am recording this series of video especially dedicated to my most amazing students in the course of electromechanical conversion systems. And when you are working with electromechanical conversion systems, specifically the direct current machine, some very important phenomenon is the induced voltage. The induced voltage in the armature of the DC generator is extremely important. So today I decide to dedicate this video for calculations regarding this induced voltage. So let's start with reading this very interesting statement. A 4-pole wave-wound armature having 45 slots with 18 conductors is driven at 1200 RPM. Considering a flux per pole of 0.16 Weber, calculate or determine the generated AMF. So this is very interesting because now we are working with the armature of one DC generator, and here is very clear in italic. You can see that we are talking about a wave-wound armature. So the first part of this MATLAB live script document, basically I am cleaning all the variables in the memory, and then I start to define the different parameters of this problem. We start over here with phi, and phi is basically the magnetic flux per pole. In this case, the unit is Weber. Then I define the total number of slots in the armature and the number of conductors per slot. Then we know that there are 4 poles and that represent 2 pairs of pole. We are using the Greek letter eta in order to represent the rotational speed in RPM, and in this case the rotational speed in RPM is 1200. So now let me present this equation. I already explained the details of this equation in the previous video, DC machine 001. But in this equation, we can obtain on the left-hand side the induced voltage in the armature in volts. And on the right-hand side, you can see the different terms, the number of pairs of poles, the rotational speed, but be careful because the rotational speed must be introduced in this equation in revolutions per seconds. You can see here the flux per pole, and in this case the unit must be Webers. Z is a very important parameter, and that defines the number of armature conductors. And finally C, as I say in my previous video and my whole classes, C is extremely important because it's defining the number of parallel paths through the winding between the positive and negative brushes. So what is important over here to you is that there are typically 2 different types of winding, the wave winding and the lap winding. And in this case, we are working with a wave winding, and you can see that the letter C is numerically equal to 2. So next step is to determine the total number of conductors at the armature. I already explained in my previous video, this is the cross section of one armature, and you can see the details of the number of conductors in the slot. However, you must remember that this is an illustrative example, because in this case we are having 45 slots at the armature, and inside each one of those slots we are having 18 conductors. So calculating the total number of conductors in the armature is a very simple numerical exercise. We multiply the number of slots, in this case 45, by the total number of conductors per slot, in this case is 18. So on the right hand side you can see the result over here. The numerical result is that we are working with 810 conductors. So now what I will do is basically we need to transform this rotational speed. The data is given in RPM, but inside the equation I need to use revolution per seconds because the units. So what I am doing is converting this 1200 RPM into revolution per seconds. So what we need to do is divide by 60, and on the right hand side you can see the answer over there. We are talking about a rotational speed of 20 revolutions per second. Finally, the calculation of the induced voltage at the armature is basically a numerical substitution in this equation that we already presented. And basically we are multiplying twice the number of poles, 2 in this case, the rotational speed, 20 revolutions per second, the flux per pole, in this case 0.016, and set divided by C. We are talking about 810 conductors and C equal to. So as you can see over here, the induced voltage across the armature is 518.4 volts. And that is the voltage that is induced in this amazing armature of this DC generator. So just to remind you, you need to be very careful about the units that you are using inside your equations. Remember, the rotational speed must be in revolution per seconds, and also be careful with this lower letter P because that represents the number of pairs of poles. So yes, we reached the end of this video. It's been a very simple example, but also allow you to understand there is a huge difference between the wave winding and the lap winding. Today we use a lap winding to produce, a wave winding to produce 518 volts. So before we finish this video, I would like to invite you to be part of our community. We are very frequently updating status and providing a lot of information on LinkedIn. Please, if you want, subscribe there. And if you are watching this video, it's because you are inside YouTube. If you like the explanation, you understand everything, please feel free to subscribe to the channel. And finally, there are 2 links over there for the social media, Twitter and LinkedIn. Please feel free to subscribe over there. Well, this has been the video today about induced voltage. This is all for this video, and I must tell you, bye now.